Well, I decided to be nice and make a video for you, so you're welcome. Let's go and take the derivative of both sides. This is on page 13. What's 12? Nope. Is this 12? See, that's 11. What's 12? Is 12 blank? I hope 12 is blank. Oh well. Oh my gosh, guys. I just realized I never answered the rest of the question. I didn't do the concavity part. Ah! Okay, let's do the concavity part and then we'll move on to the actual problems that are practice. Concavity is second derivative. So I need my second derivative of the function. So what I have to do, dy dx was equal to x over 9y. Got it. So let's do dy dx is equal to x over 9y. Okay, I need my second derivative. My second derivative will be d dx of dy dx on both sides, d dx. Okay, so what we get here is, hey look, we get d squared, d2y, and dx squared. Don't put d squared x squared, that's weird. So d2y dx squared is equal to, now we need the derivative of the right side. That's a quotient rule. Okay, and if you didn't know that, that's a quotient rule. And we have to do low d high. So we'll do low 9y times the derivative of the high function, which is 1, minus high, which is going to be x, times the derivative of the low, which is 9. Come on, 9 times what? 9 times what? 9 times what? 9 times dy dx. And the reason is because you just took the derivative of y with respect to x. So the derivative of 9y is 9. You took the derivative of y with respect to x. This is all going to be divided by 9y squared. Okay, next. Let's go and simplify this. We get 9y minus 9x dy dx over 9y squared. That's our second derivative. That's not terrible. I'll tell you that in my experience, students always miss, not always, but students, if they were to make an error on this problem, would forget that part right there. So again, what that part tells me, if I was looking at your paper or Miss Schwartz, is, "Hi, Mr. Lincoln." "Oh, hi, Miss Schwartz. Thanks for joining us." "Yeah, how's the videos going?" They're going great, Miss Schwartz. Thanks for asking. You can go ahead and leave now because you're kind of interrupting the videos. "Oh, I'm so sorry. I didn't mean to do that." "No, it's okay. Go ahead. Bye." Oh, that was Miss Schwartz. So what I'm telling you guys is that what Miss Schwartz and I have found is that if you were to make a mistake with this, you're missing the dy dx. If you're missing it, it's because you don't know what implicit differentiation is. You cannot just take the derivative of a variable and not consider what you're taking the derivative of the variable with respect to. So again, practice that dy dx and make sure you know when to put it. To answer the question, I believe our points at at x equals 5 were 5, 1, and 5, negative 1. So let's finish up this problem super quick. We have d2y dx squared at 5, 1, which is going to be equal to 9 times 1 minus 9 times 5 times dy dx when x was 5 and y was 1 was, I think, 5/9, right? Yeah, 5/9. Because I solved that part already. At the bottom was 9 times 1 squared. Let's see what we get here. We get 9 minus, let's see, these 9's cancel. So we get 9 minus 25 over 9. Okay, that's negative 16 over 9. And if my second derivative is negative, which means it's less than 0, my second derivative is negative, then the concavity at 5, 1, the function, the curve, we can't call it f, and we can't call it a function actually, the curve is CCD, concave down. And then I repeat that for the other one. So I'll have that here right now. Okay. So here's the work for the second one. You should have gotten a positive 16 over 9, which is greater than 0. So at 5, negative 1, the curve is concave up because your second derivative is positive at that point. Okay, now we can move on. So, for page 14, and again, feel free to move along. I think this is page 13, actually. Let's go and take the derivative. Again, you should have practiced this. I'm going to sound a little bit mean right now. Do not just watch this video and solve these problems without trying them first. Because if you're doing that, you're just copying down stuff and it shows nothing of what you know and don't know and what you can improve on. So please pause the video, try these first, and then actually go through the problem. So assuming you pause the video, let's take d dx at both sides. And again, no reason to actually solve for a variable because that's what implicit differentiation is for. Derivative of x cubed is 3x squared plus the derivative of xy. Well, we need first times second plus second times first. We need that product rule. So we'll do x times dy dx plus 1 times y plus derivative of y cubed is 3y squared dy dx equals 0. Don't forget the 0 part. Another common mistake that I see with this and that Ms. Schwartz sees with this is students forget that the derivative of the constant is 0. So be careful with that. Let's go and get everything on one side. That's not dy dx, and then all the dy dx on the other side. So dy dx, this time I'm going to factor it in case you weren't sure about that before, is equal to a minus 3x squared plus y. So in other words, I moved 3x squared and y to the other side. They both became negative, so I took that out. You didn't have to. And then my final answer here for this one is dy dx equals negative 3x squared plus y over x plus 3y squared. That's for number 1. Let's go to number 2. Okay, number 2. Take the derivative of both sides. The way we show that is we're going to do d dx on both sides of the equation. That tells the reader that we are going to go ahead and take the derivative of both sides with respect to x. On this side, the derivative of y is dy dx. And then, again, before you launch into it, you think of what you need. X times sine y. You need a product rule. So we have to do minus, and now the product rule will be the derivative of x, which is going to be 1 times sine y, plus, now this is going to be a tricky one, plus x times the derivative of sine y, which is going to be, so let's do some side work here. The derivative of sine of y is going to be cosine y times the derivative of the inside part, which is going to be dy, dy dx. So times cosine y times dy dx, and then this is equal to 0. Okay, so now we can go ahead and do dy dx minus sine y minus x cosine y dy dx equals 0. Okay, so it looks like we're just moving a sine y over. And again, if you feel like you can do it all in one step, go for it. Sine y is equal to a 1, because remember there is a 1 here, 1 minus x cosine of y. Again, super tricky one. The reason that's tricky is your chain rule. When you took the derivative of the inside of cosine of y, that part was going to be a implicit differentiation. So be careful with that. That one was super tricky, and again, that was a chain rule. Okay, last one, number 3. Oh, and 4. Oh my gosh, that's too much. All right, let's do 3. It's going to go to 3 here. Okay. Okay, number 3, let's take the derivative of both sides. I just realized that for those of us that are not, I'm not your teacher, I'm sorry that this handwriting is horrible. The derivative of x is going to be 1 plus the derivative tangent is secant squared of xy. And then this one is really going to be fun because you have to take the derivative of the inside. The derivative of the inside is a product rule with implicit differentiation. So first times derivative second, so it's going to be x times 1 times dy dx. This was the derivative of y. And then plus second times the derivative of the first, and on the other side equals 0. Okay, let's distribute and actually get an answer here. So 1 plus secant squared xy. Sorry, I wrote that wrong. xy, yx, same thing. Just change that though so it's consistent. Times x, so there's an x in front. And then plus, let's do another one, y secant squared of xy. And again, my students are shouting at me. Maybe you are too if you're not in my class, because I forgot the dy dx over here. So dy dx over here. No plus ones to anybody. When I solve that, I get dy dx is equal to, big fraction bar, a negative 1 plus y secant squared xy, all divided by x secant squared of xy. It's not pretty, but that is our derivative, and we can plug in any x and y value to be able to get the slope of the tangent line for that curve. Okay, and now let's go to number 4. Here it says find dy dx when x equals negative 1. Again, the first thing that's calling out to my mind is that I don't actually see a y value. Let's find the y value. When x is negative 1, we have y is equal to negative y plus 1 plus 1. The reason we have this plus 1 here is because it was negative 1 squared. So that means we get 2y equals 2, which means y is equal to 1. So first thing I needed a point. Negative 1, 1 is my point. Now I can take the derivative. When I take the derivative of x with respect to x, I get dy dx, or actually I could just write y prime equals the derivative of the first. So again, this is going to be a product rule again. So it's going to be the first times the derivative of the second plus the second times the derivative of the first. And then plus x squared, the derivative of x squared is plus 2x, and the derivative of 1 is just 0. What I should have shown you here is that I was taking the derivative of both sides with respect to x. And again, you should do that too, because if you didn't know what I was doing there before, that could be really confusing. Second thing that I want you to be aware of that I just did that I hadn't done before, y prime is dy dx. The difference, Leibniz notation, this is called Leibniz notation, actually allows you to show what derivative you're taking with respect to. The prime notation doesn't actually show that, so there is some disadvantage here. And I think I glossed over that way back here. I didn't explicitly mention that. Explicit. It was implied, but there is prime notation. There's prime notation again with f, and then there's Leibniz notation. Implicit differentiation will usually utilize Leibniz notation, but prime notation is fine. You just don't know what you're taking the derivative with respect to. Okay. So let's go back here. Y prime equals dy dx. Okay, so now let's get y primes on one side, everything else on the other side. So it looks like we're going to get 2x plus y equals, and if I move this to the other side, and I remember that there's a 1 in front of here, I get 1 minus x. And that's equal to y prime. Okay, so if I want to evaluate, well, I'm going to evaluate y prime of negative 1 comma 1. When, again, x is negative 1, y is 1. So I'll get 2 times negative 1 plus 1 over 1 minus negative 1. And that answer is going to be negative 1 over 2. My slope at that point is negative 1/2 for that curve. Okay, and then here's 5 and 6. And then I'll be done. Let's take the derivative of both sides. I'm going to get 2y dy dx, or y prime, plus 2 dy dx, or just y prime, equals, the derivative of 2x plus 1 is just 2. So dy dx, this was a little bit of an easy one, dy dx is equal to, not as cumbersome, 2 over 2y plus 2. Everything has a 2, so I can write this as 1 over y plus 1. Okay, that's my first derivative. My question is asking me to find the second derivative, so let's find the second derivative. The second derivative is going to be, let's rewrite this as y plus 1 to the negative 1. That way I don't have to do a quotient rule, because quotient rule is kind of too much work. So d2y dx squared. And again, what I'm doing here, I'll just show all my work because that's what I expect of you. I'm taking the derivative of both sides again. And that gets me here. Equals, okay. Actually, I just want to change one tiny little thing here. I'm actually taking the derivative of this part. Okay. I'm going to get, the negative 1 comes down in front, so negative 1 times y plus 1 to the negative 2 times the derivative of the inside, and the derivative of the inside is dy dx. Come on, x. Okay. And we know what dy dx is. dy dx was equal to 1 over y plus 1. So now we have negative 1 over y plus 1 squared. I don't like negative exponents, so I usually change them to positive ones when possible. Times dy dx was 1 over y plus 1, which is now going to equal negative 1 over y plus 1 cubed. My tip, I would recommend you get really, you become really good at finding dy dx's, and then after you do that, make sure that you go ahead and put, then make sure you work on second derivatives. So make sure you're good at implicit differentiation first, which means find dy dx when there's an implicitly defined function. And then once you master that, then make sure you practice that second derivative, because that second derivative is always tricky, especially when you have to do a chain rule. Okay, last one. Oh, goodness, I need to go to sleep. This one says, show that the second derivative of y with respect to x is negative 16x over y to the fifth. And I still got one more video to make. Ay, ay, ay. Okay. Hope you guys appreciate this. There you go. Last one, we got 3x squared plus 3y squared dy dx, because I'm taking the derivative of y with respect to x, equals 0. If I move everything to one side of the equation, I get negative x squared over y squared. I move the x squared over here, I divide it by y squared, and the 3 is canceled. Now let's take the second derivative. Again, now I'm going faster because I have to still make one more video. So next, we're going to get d2y dx squared on the left equals, okay, low, so y squared, because I need a quotient rule, times derivative of high, which is negative 2x, minus high, which is negative x, so plus x squared, times derivative of low, which is 2y dy dx. Okay, all divided by y to the fourth. Now, I can rubber band this, if you know that term, because each of these terms has a y in it. So I could actually rewrite this as y, negative 2xy, just one y there, plus 2x squared dy dx over y cubed. Okay, next, I have to plug in dy dx again. So this is equal to, and I need my answer to look like that. That's my big time goal. So now I got negative 2xy plus 2x cubed, 2x cubed times negative x squared over y squared. All divided by y to the third. Oh, this is going to be ugly. All right, now I'm just going to, I need more room. Can I move these? Yes. Let's just get rid of these. It's moving the whole page. This is moving the whole page, isn't it? Dang it. Alright, have no fear, Blaine. You can do it. Did I just call myself Blaine? Oh my gosh, it's so awkward. Let's go underneath this. I wrote it down here. So now we get, I'm starting to lose steam, guys. So now we go ahead and get, when we multiply all this, let's multiply both sides by y squared. And we get negative 2x y cubed plus these y squareds cancel. But again, a y squared went over here too. So we get negative 2x cubed. So that's going to be minus 2x cubed. So minus 2x cubed. All divided by y to the fifth. That's good, because I think I'm supposed to get this to look like negative 16x to the fifth. Okay, so I'm almost there. Y cubed, I want to get rid of my y's, because my answer in the top didn't have any y's. So remember, y cubed is actually equal to 8 minus x cubed by using that original equation. So if we substitute that in, we end up getting out, this is a tough problem, negative 2x times 8 minus x cubed minus 2x cubed. I really hope that's negative 16x. Okay, let's see here. Over y to the fifth. Okay, let's go ahead and do distribute. So we got negative 16x plus 2y cubed minus 2, what's an x? Hold on, I went too fast. What's the answer supposed to be? Negative 16x. And I found my mistake. My mistake was that this should be negative 2x to the fourth. So now I'm good. Which means this is minus 2x to the fourth. Which means that this is going to be plus 2x to the fourth. And then minus 2x to the fourth. All divided by y to the fifth. See, I should really stop making videos because I'm starting to make mistakes, which is not good. And then we end up getting what we wanted, negative 16x over y to the fifth. Yikes. Okay, that's it for this one. I would star 6 and make sure you do that again, and I'll do that again too, because I kind of botched that up. So again, try 6 again. That's a tough one. Thanks for watching.